ellipse. And through this arbitrary point P, I will construct the distance to the focus and the distance to the directrix. Well, how do I do this? Well, one of those is easy. I can construct the distance to the focus here. It's going to go like that. And note that that's going to be like a tangent, right?
Right.
Even though it doesn't quite look like it. And then, maybe I'll just make this a little more better. Okay, and then I can also construct the distance to the directrix. Well, the shortest path between point P and the directrix is a straight line, right?
Yeah.
But that line is in plane pi, and so is the point P being on the ellipse in plane pi. So the shortest distance from P to the directrix is along plane pi, right?
Yeah.
Okay, so I will now draw this. That could be better. Yeah. Well, okay. So that distance from P to the directrix is the distance from the point to the directrix. Okay. Good. All right. Now, according to my directions. Now, so that's right. Oh, and now what I'm going to do is arbitrary. Okay. So now I have even another I need more color for this. I will now construct the ray OP. Okay, so this ray OP, oh boy, is going, no, it'll be fine, is going to come down and is going to meet, the circle somewhere.
I like L2.
Okay, so this was circle C2. This point down here, I'm going to call L2. What is L2? It's the intersection of the ray from the vertex through the arbitrary point P on the ellipse, meeting the circle L2. Cool?
Yeah.
Okay, now, note that PF2 equals PL2.
Yeah.
Because P is an external point, PF2 is tangent to the sphere, PL2 is tangent to the sphere along the outside of the cone. So these two are equal because tangents drawn from an external point to 2 points on the same sphere are equal. So that's nice. Okay. Also, this plane, this is like L, right? This line L. This line L is like perpendicular to this plane through the circle C2. Yeah. So that's what that picture is meant to indicate. Additionally, we have that this plane pi meets the axis at some kind of angle, and in particular, this angle is the angle that the plane pi makes with the axis. We've been calling that theta. Cool? Okay, because theta has something to do with eccentricity, right? Okay, that's theta, and hence, so is this theta. Because they're like vertical angles. Everyone following this?
Yeah.
Okay, now, the distance from P to D along pi mu. Oh yeah, so this, let's call this point way out here, let's call this point P prime. P prime is the what you get when you drop this perpendicular from P to the directrix. Okay, and now I'm going to do one more thing, which is I'm going to drop a perpendicular from P down to the plane through C2. I need one more color for this. Brown. Too late. So I drop this perpendicular. That's perpendicular. And that point down there, I'm going to call G. I guess it would be a little bit lower, right? G. And G is in this bottom plane, and so is L2. So that is like a straight line. That's a right triangle.
Yeah.
Agree? Okay, you see where this is going, huh? Because PG is a perpendicular drop straight down. If PG is a perpendicular drop straight down from arbitrary points to the plane through this to this bottom plane, then that means that this brown line is parallel to the axis. Yeah?
Yeah.
Even though it looks slightly off. And if that's true, then this vertex, that's angle theta, but so is this, or alpha, I mean, that's also alpha, yeah?
Yeah.
And if that's also alpha, then that's also alpha. Okay.
Oh.
And now, there's one more thing which is also, and then this is that what I wanted to say? Sure. And the last thing is, I will connect, PG is parallel to L, check. This is also, so P theta, let me just write this down. So angle P prime PG is also theta. What is P prime PG? Oh yeah, that's also important. This is also theta. Agree?
Yeah.
Okay.
That makes
So what is the cosine of theta? Cosine theta is PG over PP prime.
Yeah.
Yep. Right? Because now I'm sort of making like this right triangle, so to speak. Right? That's also a right triangle. So if you take the cosine of theta, you get PG PP prime. Who's following this?
Yep.
Yeah.
Like everyone? Okay. Good. And now, one more thing. Here it is down here. So that's a thing. And also, so therefore I get that PG is P prime cosine theta. Put that in a box. Next, cosine alpha is PG over PL2. Why is that true? Oh yeah, that's totally true, right? Looking at that little brown triangle, cosine alpha PG over PL2. Okay, so in other words, PG is also equal to PL2 cosine alpha. Okay, and here we go. I shall now prove that this is an ellipse. Here is the proof. What do I need to show? That the ratio between the distance from an arbitrary point P on the ellipse to the focus, in other words PF2, over the distance from that arbitrary point to the directrix, PP prime, is constant. And, well, what is PF2? PF2 is just PL2. And what is PL2? It's, I don't know why, but it's just PG over cosine theta.
Yeah.
Cosine alpha, I mean. And what is PP prime? It's PG over cosine theta. In other words, it's cosine theta over cosine alpha. And this is this thing we call the eccentricity. Whoa. 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 It's an ellipse. And what eccentricity really is, the real meaning of geometric interpretation of eccentricity is it's the ratio between the cosine of the angle formed by the intersecting plane and the axis of the cone and the cosine of the vertex angle of the cone. And as those two are fixed, given a particular cone and a particular intersecting plane, then that is really what's going on. And wait, before you all leave, this actually explains like a lot of things. For example, if theta is 90, what do we get? 0, right? And when is the eccentricity 0? This is our, right, It's a circle, right? But how could theta be, what if theta is 0, then where's the directrix? It like doesn't exist, right? So the directrix is like out infinity or something like that, right? Circles have no directrices. And of course, when these angles are equal, what do we get? A parabola, which was our original definition of parabola, right? When the angles are equal. And if you look at the graph of cosine, you will see it's like decreasing on the interval from 0 to 90. And so, like, when do we get a hyperbola, or when do we get an ellipse? We get an ellipse when the top one is bigger than the bottom one, which happens when the angle theta is bigger than. Am I doing that wrong? Anyway, you can reason through let's just stop the video now, but you can reason through the various definitions of ellipse and hyperbola and see when the size of the angle is whatever it needs to be, you get the ratios being bigger or smaller.